A car traveling 106 miles on a single gallon of gasoline sounds like the death of the ordinary combustion engine. But the number hides a crucial correction. China did not build a gasoline engine that can independently carry a family sedan for 106 miles on 1 gallon. It built a hybrid system that reportedly achieved that result under a particular test, while its gasoline engine reached a separate peak thermal efficiency figure of 48.41%. Those two numbers are connected, but they are not the same achievement, and the difference between them reveals something far more threatening to Detroit than one unusually efficient engine. Because Ford, General Motors, and Stellantis can study combustion chambers, they can purchase efficient electric motors, they can develop batteries, power electronics, transmissions, and control software. What is much harder to reproduce is the system that decides, second by second, how all of those machines should cooperate. That is where Geely's real advantage may be hiding. And it matters even if you never buy a Chinese car. It could determine whether the next generation of affordable vehicles needs an enormous battery, whether traditional hybrids remain competitive, and whether decades of American engine knowledge still translate into market leadership. To understand why, the first number we need to examine is not 106. It is 48.41. A gasoline engine converts chemical energy into heat. Some of that heat becomes useful mechanical work at the crankshaft. Most of it normally escapes through the exhaust, cooling system, friction, pumping losses, and incomplete combustion. Thermal efficiency measures how much of the fuel's energy becomes useful output. If an engine has a brake thermal efficiency of 40%, roughly 40% of the fuel energy reaches the crankshaft as mechanical work at the measured operating point. The rest is lost. For a mass-produced gasoline engine, moving that figure toward 50% is exceptionally difficult. Engineers are fighting several losses at once. They need the fuel to burn quickly enough to create pressure at the right moment. They need the expanding gases to push on the piston for as long as practical. They need to reduce friction between moving components. They need to avoid pumping air through the engine unnecessarily. They must control heat without cooling the combustion process so aggressively that efficiency disappears. And they must prevent abnormal combustion, excessive nitrogen oxide emissions, unstable ignition, component damage, and unacceptable noise. Improving one area can make another area worse. Higher temperatures may improve theoretical efficiency but increase emissions and thermal stress. More exhaust gas recirculation can reduce certain losses but make combustion harder to stabilize. A longer effective expansion can extract more energy from the gases but reduce specific power. Thinner lubricants and low-friction surfaces can save energy but must still survive thousands of cold starts and years of wear. That is why an improvement of 1 percentage point can require changes across the combustion chamber, intake system, injection strategy, cooling circuit, lubrication system, materials, calibration, and manufacturing tolerances. So 48.41% deserves attention. But it does not mean that 48.41% of the fuel energy is converted into useful motion during every moment of a journey. This is where many viral explanations go wrong. An engine does not have one fixed efficiency. It has an efficiency map. Imagine a landscape covering different engine speeds and loads. Some regions are deep valleys of wasted fuel. One small region is a high plateau where the engine performs near its best. A conventional gasoline car cannot remain on that plateau. The driver may request gentle acceleration, sudden acceleration, crawling speed, high-speed cruising, cabin heating, or almost no power at all. The engine must follow those demands because it is mechanically responsible for moving the vehicle. At low load, it may waste energy pulling air past a partly closed throttle. At idle, it burns fuel without moving the car. During a cold start, friction is higher, combustion is less favorable, and the emissions equipment has not reached its ideal temperature. During rapid acceleration, The engine may enter operating regions chosen for power, temperature protection, or emissions control, rather than maximum efficiency. A record peak value therefore tells us what the engine can achieve at its best point. It does not tell us how often it can remain there. This is why Geely's result is not really the story of an engine defeating the laws of thermodynamics. It is the story of a hybrid system protecting the engine from the driver. The accelerator pedal no longer needs to command the gasoline engine directly. Instead, it communicates the driver's demand to a supervisory controller. That controller has options. It can use the electric motor. It can start the engine and generate electricity. It can send engine power toward the wheels. It can combine engine and motor output. It can recover energy while slowing down. Or it can keep the engine switched off. This separation gives the combustion engine something ordinary engines rarely receive: permission to be bad at certain jobs. An engine designed for a conventional car needs acceptable torque across a wide speed range. It must start smoothly. It must respond quickly. It must provide power even when its operating conditions are inefficient. It needs to satisfy the driver without depending completely on another propulsion device. A dedicated hybrid engine lives under different rules. The electric motor can provide immediate low-speed torque. The battery can absorb short differences between generated power and demanded power. The control system can delay an engine response that would otherwise force inefficient operation. The engine can therefore be designed around a narrower mission. It does not need to be the best machine for every second of the journey. It needs to be extremely good at converting gasoline into useful energy inside carefully selected operating regions. That opens a different engineering path. Valve timing can create an effective expansion process that extracts more work from the combustion gases. The engine can operate with strategies that prioritize efficiency over low-speed personality. Exhaust gas can be used to manage temperature, pressure, and pumping losses. Fuel injection can be shaped to create a fast and controlled flame. Internal surfaces, bearings, piston rings, oil pumps, and cooling circuits can be redesigned to reduce the small losses that become enormous when added together. None of these ideas is magic. Many are familiar to engineers across Europe, Japan, America, and China. The advantage comes from combining them without demanding that the engine behave like a traditional engine. Consider what happens in city traffic. A normal gasoline engine is asked to produce tiny amounts of power while repeatedly starting, stopping, and changing speed. These are often poor operating conditions. The engine is large enough to accelerate the complete vehicle, yet much of the time it is asked to produce only a fraction of its capability. That is like operating a large industrial generator merely to illuminate one room. A hybrid can turn the generator off. The motor handles the low-speed movement. When the battery needs energy, the engine can start under a more useful load, generate power efficiently, and stop again. The engine may burn more fuel per minute while operating, but it can burn fuel far more efficiently and operate for fewer minutes. This is one reason the electric motor should not be described as a small assistant attached to a gasoline car. It changes where the engine operates. It changes when the engine operates. It changes how the engine can be designed. And it changes the meaning of acceleration. When the driver suddenly requests more power, the motor can respond before the engine moves into an inefficient or thermally stressful condition. Electric torque acts as a buffer between human behavior and combustion. The battery performs another buffering function. Suppose the engine's most efficient output is higher than the power presently needed at the wheels. In a conventional car, the engine must reduce its output and move away from its best region. In a hybrid, some of the excess can charge the battery. Later, the stored energy can move the car while the engine is off, or support the engine during higher demand. The battery is therefore not only an energy container, it is a scheduling device. It allows energy production and energy consumption to occur at different moments. That scheduling ability is essential because the highest thermal efficiency in the world has limited value if the controller repeatedly chooses the wrong moment to use it. This leads to the next misunderstanding surrounding the Geely headline. The 106 mile/gallon figure cannot be credited to the engine alone. Vehicle mass matters. Aerodynamic drag matters. Rolling resistance matters. Electrical losses matter. Motor efficiency matters. Battery charging and discharging losses matter. The transmission path matters. Accessory loads matter. Temperature matters. The route and speed profile matter. The battery's starting and ending state of charge matter. Even a brilliant engine can produce disappointing fuel economy inside a poorly coordinated vehicle. Imagine that the engine produces mechanical energy efficiently, but the system converts that energy into electricity, stores it in a battery, retrieves it, passes it through an inverter, and sends it through a motor when a direct mechanical path would have wasted less energy. Every conversion takes a small percentage. A controller that chooses the wrong path can throw away the engine's hard-won efficiency. The hybrid, therefore, needs to answer a continuous question. What is the cheapest energy path available right now? Sometimes the answer is the battery and motor. Sometimes it is the engine driving a generator. Sometimes it is a direct mechanical connection. Sometimes it is a combination. And sometimes the best decision is not the one that consumes the least fuel during the present second. The system may need to prepare for what happens several kilometers later. A hill is the simplest example. If the controller knows a climb is approaching, it may preserve battery energy for the section where electric assistance prevents the engine from entering an inefficient high-load region. If a long descent follows, preserving too much battery charge could be wasteful because the battery would have insufficient capacity to capture regenerated energy. If the destination lies inside a congested urban area, the system may save electrical energy for low-speed operation. If the engine and exhaust system are cold, the controller may choose a strategy that warms them efficiently rather than repeatedly starting and stopping the engine. Temperature, altitude, humidity, traffic, road gradient, driver behavior, battery condition, and cabin demand can all alter the best decision. At higher altitude, the engine receives less oxygen in each volume of air. Cold batteries may accept and deliver power differently. Cabin heating can consume energy that looked available for propulsion. Cooling demands can change the most efficient operating point. A fixed control map must compromise across all of these conditions. A more adaptive system can select different compromises. This is where Geely places artificial intelligence at the center of the story. The phrase requires caution. Artificial intelligence cannot manufacture energy. It cannot raise efficiency beyond the physical capability of the engine, motor, battery, and power electronics. And without independent technical disclosure, broad claims about artificial intelligence gains should not be treated as proven simply because a company uses the label. But intelligent prediction can reduce avoidable mistakes. It can estimate what the vehicle is likely to need. It can identify operating patterns. It can adjust energy allocation using environmental information. It can decide whether one efficient engine run now will prevent several inefficient engine starts later. Even a tiny improvement in thousands of decisions can matter over an entire journey. This changes the competition. The old engine battle was fought mainly inside metal. It was fought through compression, combustion, airflow, lubrication, cooling, metallurgy, machining, and exhaust treatment. Those disciplines still matter. But the hybrid battle is also fought in timing. Two manufacturers may possess engines with similar peak efficiency, use motors with similar electrical efficiency. Their batteries may contain similar usable energy, yet one vehicle can consume less fuel because it makes better decisions about when each component should operate. The difference may not appear on a conventional specification sheet. Horsepower will not reveal it. Battery capacity will not reveal it. Peak thermal efficiency will not reveal it. The advantage appears only when the complete system moves through changing real-world conditions. That is why Detroit cannot solve this challenge merely by examining Geely's combustion chamber and producing a similar piston. The combustion hardware is only the first layer. Below it sits the electric drive. Below that sits energy management. then thermal management, then navigation and environmental prediction. Then the vehicle's electronic architecture. Then the development system that collects information, changes calibrations, validates those changes, and moves them into production. This creates an uncomfortable possibility. The famous 48.41% engine may not be the component American manufacturers should fear most. The harder detail to copy may be the invisible structure deciding when that engine is allowed to exist at all. Because that invisible structure determines whether every expensive mechanical improvement is used intelligently or wasted. The engine may contain the most impressive number, but the electronic architecture decides whether that number matters outside a laboratory. In an older vehicle, electronic control units often behave like separate departments inside a large company. One computer controls the engine, another controls the transmission, another manages the battery, others handle braking, steering, climate control, navigation, safety systems, and driver assistance. They exchange information, but each controller may come from a different supplier, operate on different software, and protect its own section of the vehicle. That arrangement can work reliably. It can also make deep optimization painfully slow. Imagine that the hybrid controller wants to predict how much battery energy should be saved for a hill ahead. It may need map information from the navigation system. It may need the battery temperature from the thermal controller. It may need expected cabin cooling demand. It may need traffic information. It may need the engine's current temperature, the battery's state of health, the road gradient, and the driver's recent behavior. If those signals are trapped inside separate electronic islands, the powertrain can only make a limited decision. The hardware may be capable of extraordinary efficiency, but the software cannot see enough of the vehicle to use it. Geely's argument is that its newer electrical and electronic architecture gives the energy management system a wider view. Instead of treating the engine, battery, electric drive, navigation system, and onboard computers as loosely connected products, the company can treat them as parts of one energy network. That does not mean every decision is made by one giant computer. Safety-critical systems still require separation, redundancy, and predictable behavior. But information can move more freely. Software functions can be coordinated at a higher level. And the vehicle can make decisions based on what the complete machine is about to experience, rather than what one sensor detected a moment ago. This is the first detail Detroit cannot simply copy by opening the bonnet. The architecture is not a visible component. It is a set of communication standards, computing platforms, software layers, supplier agreements, safety rules, data structures, and engineering responsibilities. Changing one part can affect dozens of systems. An automaker cannot replace that structure as casually as it replaces a turbocharger. A new electronic architecture can require years of development. Every control path must be tested. Every failure mode must be considered. Every update must be protected against corruption and cyber attack. The brakes must still operate when another computer crashes. The engine must remain safe if a sensor sends impossible information. The battery must be protected if communication disappears. The vehicle must behave predictably in heat, cold, altitude, rain, vibration, electromagnetic interference, and millions of unusual combinations. Engineers may never see during ordinary testing. This creates a strange reality. A young vehicle platform may be easier to improve than an old, proven one. The old platform contains years of validated hardware and dependable supplier relationships. That sounds like an advantage, but it can also contain layers of electronic decisions made for vehicles that were never designed to think as one machine. Replacing those layers risks breaking systems that already work. The manufacturer must protect old investments, existing factories, dealer tools, service procedures, software contracts, and models already under development. A company starting with a newer architecture carries less history. It can design the information flow around electrification from the beginning. This does not make Chinese engineering automatically superior. It means the starting conditions are different. Detroit's greatest obstacle may not be ignorance. It may be inheritance. American manufacturers know how to create efficient combustion engines. General Motors produced advanced two-mode hybrids. Ford developed successful power-split hybrid systems. Chrysler, now inside Stellantis, has worked with electrified transmissions and plug-in vehicles. American engineers understand predictive control, vehicle simulation, power electronics, thermal management, and engine efficiency. The scientific ingredients are not secret. The question is how quickly those ingredients can move through a giant industrial organization and become an affordable vehicle. That is where development speed becomes a technical feature. Suppose engineers discover a calibration change that reduces fuel consumption by 0.5%. Before releasing it, they must prove that it will not increase emissions beyond legal limits. They must test whether it causes rough starts in cold weather. They must check battery temperatures in mountain driving. They must confirm that the transmission remains smooth. They must validate diagnostic systems. They must ensure that the change does not create excessive wear after 100,000 miles. They must test different fuel qualities, production tolerances, driver styles, road surfaces, and component ages. The idea may be simple. Proving that it is safe across millions of vehicles is not. Now imagine repeating that process across separate suppliers, separate controllers, and several generations of electronic hardware. The organizational delay can become larger than the engineering delay. A tightly integrated company can sometimes close that loop faster. It can collect field data. It can identify where the vehicle is operating inefficiently. It can reproduce the condition in simulation or testing. It can change the control strategy. It can validate the change. And where regulations and hardware allow, it can distribute new software. This does not mean every over-the-air update produces dramatic fuel savings. Most improvements would be small. Some would address drivability, reliability, diagnostics, or safety instead. But small improvements compound. A better engine start decision saves a little fuel. A better battery temperature estimate saves a little more. Improved regenerative braking captures energy that would otherwise become heat. A more accurate road gradient prediction preserves battery charge for a climb. A revised cooling strategy reduces pump and fan demand. None of these changes makes a spectacular thumbnail. Together, they can separate two vehicles built from apparently similar hardware. Fleet data makes this loop more powerful. A laboratory can test thousands of scenarios. A large vehicle fleet can encounter millions. Drivers accelerate differently. Cities have different traffic rhythms. Mountain routes create different battery demands. Extreme heat changes cooling requirements. Extreme cold changes engine warm-up and battery behavior. Fuel quality varies. Road surfaces vary. Components age. Software that performs perfectly during a certification cycle may behave differently when an actual owner makes 5 short journeys, parks for several hours, climbs a hill, and then switches on maximum cabin heat. Fleet data can reveal those patterns, but data alone is not an advantage. The company must know what to collect. It must obtain permission to use it. It must protect customer privacy. It must transmit and store the information securely. Its engineers must convert the data into a useful diagnosis. And the organization must be capable of changing the product afterward. Otherwise, the company owns a mountain of numbers and learns almost nothing. This is why calling the system artificial intelligence can both explain and distort the achievement. The useful part is not a mysterious digital brain inventing energy. It is the ability to examine more variables, recognize patterns, predict near-future demand, and improve control decisions. The dangerous part is assuming that the label proves every claimed saving. An AI controller can make a good prediction. It can also make a bad one. A route may change unexpectedly. Traffic information may be wrong. The driver may suddenly accelerate. Weather conditions may differ from the forecast. A model trained on one region may perform differently in another. The vehicle must therefore remain efficient and safe when prediction fails. That requires conventional engineering underneath the intelligence. Fallback strategies, physical limits, diagnostic monitoring, conservative battery protection, deterministic control where uncertainty is unacceptable. The intelligence can advise the machine. It cannot be permitted to gamble with the machine. And Geely's technical story is not entirely Chinese in the simple national sense suggested by the headline. The engine program has been linked to Horse Powertrain, the joint venture built from powertrain assets associated with Geely and Renault, with Saudi Aramco holding a minority stake. Horse combines engineering organizations, factories, intellectual property, and combustion experience from several industrial histories. Its operations include former engine development capabilities connected with Geely, Renault, and Volvo. This matters because modern automotive competition rarely follows a clean national border. A Chinese-branded vehicle may use engineering developed by multinational teams. An American-branded vehicle may depend on batteries, semiconductors, motors, or software developed across Asia and Europe. A European company may share a transmission with a Chinese partner. The decisive advantage may belong to the company that coordinates the network, not the country that claims every invention. Geely does not need to create every piston coating, chip, motor winding, algorithm, and manufacturing tool alone. It needs to assemble those capabilities into a product faster than competitors. That is a different form of industrial power. It also explains why the phrase, "Detroit cannot copy it," must be handled carefully. Detroit can copy the physics. It can benchmark the combustion process. It can measure valve timing. It can analyze the cooling system. It can examine the electric drive. It can create a predictive energy controller. It can build a vehicle with equal or greater peak engine efficiency. What it cannot copy instantly is the path that produced the machine. It cannot purchase years of fleet learning in one transaction. It cannot immediately simplify old software contracts. It cannot move factories beside a new supplier network overnight. It cannot erase the cost of supporting millions of existing vehicles. It cannot instantly change how engine teams, battery teams, transmission teams, purchasing departments, safety engineers, software developers, and outside suppliers share responsibility. Those are not excuses. They are the actual battlefield. But before declaring victory for Geely, the 106 mile/gallon figure needs one final examination. The Emgrand's reported consumption of 2.22 liters per 100 kilometers came from a particular highway or real road test associated with a Guinness World Record claim. That is impressive. It is not identical to an official United States Environmental Protection Agency fuel economy rating. A record attempt is designed to produce the lowest possible consumption under defined conditions. A regulatory cycle is designed to create a standardized comparison across vehicles. Real owners create something messier than either one. The difference can be enormous. Vehicle speed is critical because aerodynamic resistance rises rapidly as speed increases. A car traveling at a moderate, steady speed may use far less fuel than the same car moving quickly, accelerating repeatedly, or sitting in congestion with climate control operating. Temperature matters because cold engines and batteries waste more energy. Wind matters. Tire pressure matters. Road gradient matters. Vehicle load matters. Air conditioning demand matters. The test driver matters. The energy already stored in the battery matters. For a fair hybrid measurement, the battery's state of charge at the beginning and end must be considered carefully. A vehicle can appear extremely efficient if it finishes with less stored electrical energy than it started with. That does not automatically mean Geely's test used an unfair method. It means the exact procedure matters. Without the full test documentation, 2.22 liters should be described as a verified or reported record result under specific conditions, not as the guaranteed experience of every owner. There is another important clue. Geely's larger hybrid vehicles are not expected to deliver the same number. The engine may be similar. The control philosophy may be similar. But a heavier sport utility vehicle requires more energy to accelerate. It presents a larger area to the air. Its tires may create more rolling resistance. It may carry more equipment and demand more cooling. The record therefore belongs to a complete configuration, not merely to the engine. That does not weaken the engineering. It tells us where the achievement truly exists. The combustion engine contributes an exceptionally efficient source of energy. The electric motor controls short bursts of power. The battery separates energy production from energy demand. The transmission chooses how power reaches the road. The body reduces the energy required. The software schedules the complete process. Remove one layer and the headline begins to collapse. This is also why the technology could be more important than the record itself. Even if an ordinary owner never sees 106 miles per gallon, improving the complete system could still reduce fuel use meaningfully across millions of vehicles. A 5% improvement repeated across a large fleet may save more fuel than one spectacular demonstration. And conventional hybrids remain strategically important because they do not require every buyer to install a charger. They can reduce fuel consumption in apartments, rural areas, developing markets, and regions where electrical infrastructure is limited. They use smaller batteries than full electric vehicles. That can reduce cost and material demand. They also preserve dependence on gasoline, oil changes, exhaust systems, and complex mechanical maintenance. They are not a complete solution to every emissions problem, but they can become a powerful transitional product. This is the threat Detroit must evaluate. Not that China has discovered a forbidden combustion secret, not that every Emgrand owner will automatically achieve 106 miles per gallon, and not that American engineers have forgotten how engines work. The threat is that Chinese manufacturers are learning to combine mature technologies faster than traditional competitors can reorganize around them. An efficient engine is valuable. An efficient motor is valuable. A good battery is valuable. But the company that coordinates them as one adaptive system can extract more from every component without making any one component miraculous. That is the detail hidden inside the headline. It is not a piston shape that Detroit is physically unable to machine. It is not one patent that American companies are legally forbidden to use. It is not artificial intelligence producing free energy. It is a development system in which combustion engineering, electric propulsion, software, vehicle data, supplier capacity, and manufacturing feedback are connected tightly enough to improve together. Detroit can copy that. But copying it would require more than a new engine. It would require changing the organization that builds the engine, the architecture that controls it, the suppliers that support it, and the speed at which the entire vehicle learns. And by the time that transformation is complete, Geely may no longer be defending a 106 mile per gallon record. It may already be teaching the next generation of vehicles how to use even less.